Hey guys, welcome back. Fred here from Math and Engineering. This is a continuation of the first part of our video, of a series of videos that we're doing on one-way slab design according to the Canadian Concrete Code. So if you haven't seen the first video, go back, check it out. It's in the description, it's in the comments below. We do a lot of explaining in terms of like what's going on and how we take a look at one-way slabs. So don't just start with this video. If you're here from the first video, welcome back. I wrote some information down. So we found the factored moment at the center of the slab, okay, where the maximum bending moment occurs, the maximum positive bending moment. So that's what we're going to design for. Okay, we're designing for a 1 meter strip of the slab because it's one way. We're going to use 15 M bars for flexure. Our cover's 25 millimeters. The minimum thickness was actually 270, but so we said that our slab thickness is going to be 300. Okay, and we also calculated our effective depth to be 270 millimeters in the last video. So I wrote down a couple properties as well that we had from the last question that are over here that we're going to use. So let's get right into the question and let's pick up from where we finished in the last video. We're going to calculate our area of tension reinforcement. And we're going to do that using our factored moment. Okay, so our factored moment, we're going to say that our factored moment equals our moment resistance. We're going to plug it into the formula and we're going to get the area of steel that we require for a 1 meter strip of slab. Okay, so if you'll remember, say we have some rebars here, we don't know how many yet, and this is a 1 meter strip, okay, in this direction here, and this is kind of like our 1 meter strip here, and this is our height of our slab, which is 300, okay? So that's just some info there. So the formula, according to the Canadian code, is it's quite long, and it's actually derived using Fy equals 400, and alpha 1 is equal to 0.8, and also phi c is equal to 0.65. So if you don't have these things, you need to go ahead and use the longer version. I'm not going to include it here because it's very rare that that comes up. There's also a table method using Kr that you can use, but for now we're just going to use this formula, and then we're going to check the shrinkage value, and we're going to compare them. So let's go ahead and I'll write down the formula for you here. So what we have here is we have AS, which is the required amount of steel for some width that we choose. So B is our width, okay? F prime C is F prime C, that's given, that's the compressive strength of the concrete. D is our effective depth. MR is MF, which is our design moment. The section, see this section here that we took? That's the section that we're designing for. And F prime C and B are the same there, okay? So what I do suggest, by the way, guys, is take this formula, okay, and put it into your graphing calculator. We have a really good video, I think, on how to program your graphing calculator for formulas like this. I highly suggest that you use it. I used it in my concrete courses, and it really saved a lot of my time, and it made sure that every single time I put a big formula like this into my calculator, I wasn't getting any wrong answers, and it saved me time. It gives you time at the end of the test to go back and just double check your answers and make sure that everything's right, and you never have to worry about what you got for this. So I'll link that video as well, but go check it out. I really do highly suggest that. That's a good play. So let's plug into this formula and see what we get. So here we're using B is 1000, so that's our 1 meter depth. Now at this point our MR is equal to MF, which is 67.5. Don't forget to multiply by 10 to the 6. That's a very common mistake here, okay, because we're turning it into Newton millimeters, which is what all the other units are here. These are all MPa. And if we go ahead and we put this into our calculator, we're going to get that our required area of steel, okay, is equal to 750 millimeters squared, and that is per meter. Okay, so per meter strip, in the long direction, we are required to provide 750 millimeters. Now, this is one requirement that we need to satisfy, but we also need to compare this to the amount of horizontal shrinkage reinforcement that we need to provide according to the code. So if you may have a different value in your country. For Canada, our AS for horizontal shrinkage is simply 0.002 AG, where AG is the gross area of the area that we're considering. So in this case, our gross area is 300 by 1000 millimeters. Okay, so we're going to fill that in. Okay, and that's going to give us 600 millimeters squared per meter. We're going to go ahead, we're going to compare these two values, and we're going to see which one's bigger, and we're going to design for that one, okay? So as we can see, the required amount of steel according to our formula here is greater than the amount of steel we need to provide for horizontal shrinkage. So we can go ahead and just say that we will use 750 millimeters to design with. As we were given in the question, we're using 15 M bars for flexure. That's a metric system measurement. 15 is the nominal diameter. Okay, and the area for a 15 M bar is simply 200 millimeters. If you ever want to check, you forget on the test or something, you didn't write it down, just do pi d squared divided by 4. So 15 squared times pi divided by 4. And as you can see, the code kind of rounds off the numbers, but it'll give you a general idea of what the area of one bar is. So we're going to take 200. So we're going to say and let's just separate this now. So we're going to go ahead and the area of a bar is equal to 200 millimeters. Okay, and we're going to find the required bar spacing. So we need to space the bars, and we need to space the bars also according to the code. So there's a minimum and a maximum that we are allowed to space the bars at. So let's go ahead and let's check that. So the spacing, okay, must be less than or equal to, and this is just the formula here. All we do is we're taking the area of a bar, okay, and we're going to multiply that by B, which is 1,000. And we're going to divide that by the amount of steel that is required. Okay, so that's 750. Okay, if we go ahead and plug that in, we're going to get 267 millimeters. And just to round that off to a round number, okay, you're never going to specify a spacing of like 267 millimeters. Okay, we're going to round it down. So just to be safe, that'll actually give us extra steel, and we're going to give it a nice round number so that, if you give people directions on the site for rebar, you're not going to say 267.6 millimeters because, they're not going to like you anymore. So you give nice round numbers and just round down so that it's safe and it's easier to place on the site. By the way, this formula here, I'll just write this down for you. This is simply AB times B over AS, okay? Just in case you don't know where that came from. So now that we know our spacing, okay, and we need to go ahead and just calculate what our area of steel is going to be now. So now that we have a spacing at 250, okay, and we're doing a 1 meter strip, that means that we're going to place 4 15 M bars, okay, per meter. So let's go ahead and recalculate the amount of steel. So we have 250 millimeter spacing per 1 meter strip, okay, 1, 2, 3, 4. So that is, we have 4 bars, each one is 200 millimeters squared, okay, so because we can fit 4 bars in a meter if we do them at 250. Okay, so now our area of steel is 800 millimeters squared, and that's per meter. Perfect. So now that we have our required amount of steel per meter, so the next step and the final step for this video, we're going to go ahead and we're going to calculate the reinforcement ratio rho. Okay, so we're going to go ahead and we're going to check for the max tensile reinforcement, and we're going to go ahead and find the ratio of rho. So the ratio of rho, okay, is simply just the area of steel divided by the base, which is 1 meter, times the effective depth. Okay, and we're going to compare that to a value called rho balanced, and we're going to make sure that our rho is less than our rho balanced. Okay, so I'll explain what that means in a minute, but let's just go ahead and plug in. So let's take our 800 millimeters, okay, and we're just going to divide by 1,000 times D, which is 270. And we're going to get that rho is a small number. It's 0.003. Okay, so that's 0.3% steel. So if we go ahead and take a look at the table that I just put up on the screen, you'll see that at rho B, which is the balanced reinforcement ratio, for F prime C equals 25 MPa, we're going to call that rho B, is equal to 0.022. Okay, so in this step, what you need to do is you need to check that your rho, your value of rho, okay, is less than your value of rho B. And as we can see, rho is less than rho B. Okay, so what does this mean? Well, when rho is less than rho B, that means that we have a condition which is called steel-controlled failure. Okay, and if you're unsure what I mean by this, okay, we did a video where we explain the different types of failure modes in concrete. Okay, so I highly suggest that you check that out. I'm going to put it in the description for you. This is an important concept, though, and essentially what we're doing is we're checking that we don't have a concrete controlled failure. Okay, so we're checking that what is going to yield is going to be the steel, not the concrete first. Because if the concrete fails first, what we have is a very sudden, brittle failure of the slab, which is not what we want. Okay, we want a slow, ductile controlled failure. So if we look at like the strain diagram in blue, if we write the steel controlled failure, we have a linearly elastic portion. This is our stress and our strain diagram. Okay, that is kind of the shape. And if we look at our concrete, okay, our concrete is just going to kind of fail suddenly. Okay, not exactly like that, but that's generally kind of the idea. Is that when we compare row to row B, okay, we're making sure that we have a steel controlled failure. So that's really important to check. And that's going to be it for this video. We'll probably do 3 or 4 parts. In the next video, we're gonna go ahead and we're gonna make sure that our spacing fits the minimum requirement for spacing within the slab. Then we're gonna go ahead, we're gonna check the crack control, and then we're gonna do some detailing of the slab. So yeah, that's it for this video, guys. If you enjoyed the video, hit that like button, hit the subscribe button, and stay tuned for the next part of this series. Thanks for watching, guys.